Good morning, students. Today we are going to discuss about module number 2, that is distance production. Here we are going to discuss about that reach of distance relays, effect of line length and source impedance on performance of distance relays. So let us discuss about that reach of distance relays. A distance relay operates generally when the impedance of the relay is less than the preset value. This preset impedance depends upon the corresponding distance between the fault location and to the relay is called reach of the relay. In other words, it is the maximum length of the line up to which the relay can protect. Distance relays have underreaching and overreaching tendencies depend upon the fault conditions and especially with the effect of arc resistance. When a distance relay fails to operate even when fault point is within its reach, but it is at the far of the protected line, hence it is called as underreach. The main reason or the strong reason for underreach is the presence of arc resistance within the fault. So now we are going to discuss about that underreach of distance relays. The tendency of the distance relay, whenever the amount of the impedance which is less than that preset value, the amount of the impedance whenever we are calculated between that fault location and the relay location, if that impedance is directly proportional to the length of the transmission line between fault location and relay location, if that impedance is less than the preset value, then it is known as underreach. For underreach distance relay, the characteristics are looks like as shown in the below figure. Here, in case of an underreach of distance relay, the impedance characteristics lies within the circle, even for the fault location, and the amount of the impedance, that is fault location impedance ZF and ZF plus R. Here R is showing at the adjacent side in the right angle triangle, that is that amount of the resistance from the fault location to the relay location, and the impedance offered from fault location to relay, that is ZF, which has been shown in the opposite side, and in the hypotenuse side it is showing that the sum of these fault location impedance plus resistance which was offered at the adjacent side, that is offered at hypotenuse side, that is ZF plus R. If ZF plus R characteristics lies within this characteristics or within this characteristics of this relay, then the relay will function as a underreach relay. If these characteristics lies more than this operating characteristics which shown in the circle like structure, then it is called as overreach relay. So in case of underreach relay, even though the arc resistance which was caused by the time of fault condition, if that value, the magnitude of ZF plus R which lies below the characteristics of that circle, hence it can be called as a underreach relay. Underreach relay we can applicable for impedance relay at moderate characteristics, for reactance relay none of the characteristics, for more relay it will shows that maximum amount of the impedance, for quadrilateral relay it doesn't shows any impact. Then overreach of the distance relays. The tendency of a distance relay to operate at impedances larger than its preset value, that means whenever the fault happen in any transmission line in an unit production, that is distance production, by that time the length of the transmission line which was offered from fault location to the relay location whose impedance value is greater than the preset value, because of that arc resistance, if the overall impedance which is greater than the preset value, then the operation of the distance relay is called as overreach relay. In case of overreach relay, the characteristics shows which is greater than that of the operating characteristics which has been shown like a circle like structure at here. Whenever the operating characteristics which has been cross this circle like structure, then the relay is called as overreach relay. In case of overreach relay, the current or the RMS value of the fault current is because of with DC harmonics and without DC harmonics. With DC harmonics, that the magnitude of I is equal square root of IA square plus square root of IDC square. Without DC harmonics means it is I is equal IAC. Why DC at here? Because of the short circuit condition, there is a harmonics, or otherwise we can say it as a DC transients. With DC transients there is a current, without DC transients there is a current. So with DC transients, without DC transients, these are the mathematical formula for analysis purpose what we are using at here. I is equal square root of IAC square plus IDC square. This is for with DC harmonics. I is equal only IAC, it is without DC harmonics. So now without DC harmonics, what is the amount of the impedance which was offered between the fault location to the relay location? That is DC offset. With DC offset, the impedance Z of is equal V by I. Then V by I means square root of IA square plus ID square. Without DC offset, without DC offset means without DC harmonics. Without DC harmonics, then the impedance Z is equal V by I. Here I is nothing but IAC. Whenever at these two cases, that means if you look about that with DC harmonics, without DC harmonics, at this case, with DC harmonics impedance, without DC harmonics the impedance, if you compare with DC harmonics impedance value is less than that without DC harmonics impedance. So this is the case how we can conclude that overreach distance relay, how it will perform. When the amount of impedance Z without DC harmonics is greater than that amount of the impedance with DC harmonics, then overreach distance relay will function. Then what about the transients in case of an overreach relay? The transients in the overreach relay, it can be defined as like the difference of DC offset impedance to with DC impedance to the without DC impedance, like regulation how we are calculated in the same manner. Here the formula Z off minus Z naught divided by Z naught into 100. Here Z off is nothing but the maximum impedance for which the relay will operate with an offset, with an DC offset. Here Z no offset, that is the maximum amount of the impedance for which the relay will operate for a pure symmetrical AC for the same adjustment. Here theta is equal tan inverse of x by r, that is the amount of the phase angle difference between Z off and Z no off. Next we are going to discuss about the effect of line length and source impedance on distance relays. The effect of line length, actually the amount of impedance is directly proportional to the line length in case of distance relays, that is the amount of the distance which was offered from the fault location to the relay location, whose line length is directly proportional to the impedance value Z in case of an impedance relay or in case of a distance relay. Now here we are going to discuss about what about that effect of line length and the impedance on distance relays with respect to the fault. So with respect to the fault, to discuss about this concept, let us consider an equivalent circuit diagram or one line diagram of the system during fault condition. So here the figure what I am showing, it is nothing but one line diagram of the system during fault condition. Here it is the source voltage E and Zs is that thing but source impedance, and this is nothing but point of the location of relay, and V is nothing but amount of the voltage with respect to the relay location, and ZL is called as transmission line impedance, and F is nothing but the fault which is far away from the relay location, what I am showing in the one line diagram of the system during fault condition. With respect to this diagram here, I am showing that what about that impedance of the transmission line with respect to relay and with respect to the fault. If you see that the amount of the impedance with respect to the relay and with respect here, E is nothing but the source voltage here, Zs is nothing but the amount of the source impedance from the location of relay to the source, and ZL is the amount of the impedance from relay location to fault location F, and V is the overall voltage. V is the amount of the voltage at the relay location. So with respect to this diagram, now I am going to show that the current which is flowing in this single line diagram, what I am showing, the amount of the current which is flowing in the figure here, that is I is equal to its source voltage E divided by overall impedance of the transmission line, that is ZS plus ZL. Then what about the relay location voltage? The relay location voltage V is equal its current into ZL impedance, because we are going to take in that only impedance of ZL, because relay is located after ZS. So here V is equal I into ZL. Here V is equal I into ZL, mathematically what we wrote the formula, but here I means we know that E by ZS plus ZL. Here I am substituting the place of I. Here this is the formula what I am getting here. If I am sending this numerator ZL to the denominator, if you do the simplification here, V is equal E divided by ZS plus ZL plus 1. Now this is the amount of the voltage at the relay location, and here I am showing that characteristics of that relay, that is effect of line length and source impedance on distance relays. What about that effect of line impedance and source effect? So if you see that effect of line impedance and source effect in this XR plane, in this XR plane, R is taken at real axis and X is taken on the reactance axis or Y axis, and this is the operating characteristics of the power surge characteristics, and these are the operating characteristics of A, B and the line. These are called as operating characteristics of the impedance relay. The operating characteristics of the impedance relay, if it less than that of the circle, then it shows that the relay has been functioning. If the operating characteristics lies above the amount of the impedance which has been shown above that operating characteristics of the impedance relay, then the relay can be act as a overreach relay. Now if you see these characteristics, then the relay will trip. The relay will trip especially when it is out of this XR plane. So for the characteristics of A, B, the relay will trip. If it is in the XR plane and within the circle, then the operating characteristics, that means the operating characteristics of this impedance relay will trip. Within the line means it will protect, out of the line means it won't protect. Now according to that, manufacturers of this distance relays, generally they are going to choose that the value of Moore relay or induction cup relay, we have to energize that relay with an 8 volts within 5% of accuracy. Then if we apply that V is equal 8 volts, the applied voltage is left hand side, I am substituting here V is equal 8 volts. 8 volts is equal E divided by ZS divided by ZL plus 1 in the formula. Here E can be taken equal to the normal secondary CT voltage. Normal secondary CT voltage, it is always 110 volts. So in the place of E I am substituted that 110, then the above formula can become as 8 is equal 110 divided by ZS divided by ZL plus 1. Here ZS by ZL, if I am sending that side, and 8 if I send, then it becomes 110 by 8, and again this plus 1 I am sending this side, that is minus 1. Now ZS by ZL is equal 110 divided by 8 minus 1, it becomes 13. Whenever that the overall impedance value, which is, that is ZS by ZL value, less than that 13, the relay will operate. If it is more than 13, ZS by ZL value of distance relay, if it is less than 13, the relay will operate. If it is more than 13, the relay will won't operate. With 8 volts of electrical power supply, the relay will fail to operate. So according to this principle here, the relay will function and appropriate protection has been takes place, and we are isolating that faulty section of the system and healthy section of the system. Even we can perform the same operation, the relay, where it is energized with 3 volts. By the time it has to perform with 36. If it is ZS by ZL value is less than 36, it will function. If it is greater than 36, it won't function. Thank you.